Hello students, in this session we shall discuss the first sensor in these three types of sensors, LVDT. In next session we will see strain gauge and piezoelectric. So LVDT is a very important type of sensor. It is used in many applications. We have very good LVDT in our mechatronics lab as well as in metrology lab. Metrology lab also you can find LVDT. In mechatronics lab you are going to do a few experiments in next year. While doing your hydraulics and pneumatics lab, there we have included sensors also. You can practice LVDT while doing that subject. For now we will see the theory part of LVDT. So these are the topics we have discussed in the regular classes, and in last online class vibrometer and accelerometer we have discussed, and today let us complete the LVDT. Strain gauge and piezoelectric I am splitting into three sessions here. I will again I will deal those two topics, strain gauge as well as piezoelectric sensor. In coming sessions we are going to do diaphragm, capsule and bellows. These are actually used with another sensor like strain gauge or LVDT. It can be retrofitted and it is used to measure pressure. So that is the last topic in this unit. We will discuss that also. So LVDT it is a passive type of transducer, the linear variable differential transformer. So don't say it is a transducer while expanding LVDT. L is linear, V is variable, D is differential, and T is transformer. Don't get confused with transducer. Even though it is a transducer, but it should be called as a transformer. It works on transformer principle, and it is a passive type of transducer. It requires external source to activate this sensor. The LVDT is an inductive type sensor, inductive type transducer to translate the linear motion into electrical signals. So the linear motion of the core that I will show you, and that will be transformed into electrical signals. The transformer consists of a single primary winding P and two secondary windings, and they are named as S1 and S2, wound on a cylindrical former. So the secondary windings have equal number of turns and are identically placed on either side of the primary winding. The primary winding is connected to an alternating current source. So I will show you its setup. The movable soft core iron is placed inside the former. So the displacement of the former is directly applied to the arm and attached to the soft iron core. In practice, the core is made of high permeability nickel iron. So please remember these materials. If you write material name and underline it, it will give very good impression and you will get full marks. Which is a hydrogen annealed. This gives low harmonics, low null voltage and high sensitivity. So it should be annealed, hydrogen annealed material, and this gives low harmonics. Harmonics, there are unwanted interferences or unwanted frequencies acting on the winding, and that can be minimized. And low null voltage, low null voltage is maintained when the core is at exactly middle of two secondary windings and have high sensitivity. This is slotted longitudinally to reduce eddy current losses. The assembly is placed in a stainless steel housing, and the end lids provide electrostatic and electromagnetic shielding. So shielding should be done. So that is another disadvantage with LVDT. it should be properly shielded. And the frequency of AC supply applied here to primary windings may be between 50 Hz to 20 kilohertz. Since the primary is excited by an alternating current source, it produces an alternating magnetic field, which in turn induces alternating current voltage in the two secondary windings. So this is the diagram. So this is the core. You can see core coil assembly, and you can see on either side the secondary windings. The primary winding is in the middle, and the core is at exactly middle. The null voltage is maintained, and core is it is maintained within the cylindrical space. So where the core is made to move, and it is the cross sectional view. And if you wanted to draw this view on paper, please use this diagram. So secondary windings S1 and S2, and primary winding P, and soft core iron is attached to the element for which the displacement is being measured. So the arm is attached to the object for which the displacement is being measured, and when that object moves, the iron core also moves, and that will induce the current on secondary coils. Secondary coils will be when it moves towards right side, more voltage will be induced in the secondary coil. When the iron core moves on the left hand side direction, more voltage will be induced here in secondary coil S1. So this is the simple diagram. The output voltage of secondary S1 and S1 is ES1, and the that of the S2 is ES2. So output voltage from secondary coil 1 and 2 is respectively named as ES1 and ES2. In order to convert the output from S1 and S2 into a single voltage signal, the two secondaries S1 and S2 are connected in series opposition. The output voltage of the transducer is the difference of the two voltages. The differential output voltage is equal to ES1 minus ES2. So the total output voltage is ES1 minus ES2, and when ES1 is equal to ES2, so that is the null position. In null position, it is ES1 is equal to ES2. If the core is moved to the left of the null position, more flux links with the winding S1 and less with the S2. According to the output voltage ES1 of the secondary winding S2 is more than ES2. The output voltage in secondary winding S2. So that is ES1 will be more and ES2 is less. The magnitude of output voltage is thus E0 equal to E0 is nothing but output voltage ES1 minus ES2, and the output voltage is in phase with say primary voltage. So similarly, if the core is moved to the right of the null position, then ES2 minus ES1 is the output voltage and is 180 degree out of phase. So at the extreme right hand side direction, the phase, it is known as 180 degree out of phase with the primary voltage. So it is now connected with ES2. Therefore, the two differential voltages are 180 degree out of phase with each other. So this is another term you have to use. So on left hand side, if it is extreme position of the left hand side, then it is considered as 180 degree with the secondary winding, and if it is right hand side direction, it is considered to be 180 degree out of phase with ES1. So variation of output voltage with linear displacement of an LVDT. So there is a graph, it will be more clear with this graph. The curve is practically linear for a limited range. So this is the graph. So up to little range, up to this range, it is a linear curve. So now On left hand side, if this is the 180 degree, right, phi is equal to 180 degree, and now it is phi is equal to 60 degree, and from here you have to measure to 180 degree phase shift. It is nothing but phase shift, and the curve is practically linear for a limited range. So up to here on both sides, so up to a certain range of core movement, it is actually a linear curve. Later on, it becomes a non-linear curve from the null position. Beyond this range, the displacement, the curve starts to deviate from the straight line. So here it starts deviating to either up or down, and here it is shown as down. So it becomes a non-linear curve. So displacement against output voltage, this graph on negative side and also on positive side. So now for it is the position on the right hand side, and this is the position on the left hand side of the core, and ES1 and ES2 are considered here to be at 180 degree phase shift. So very similar to LVDT, there is a rotary variable differential transformer. So instead of having a linear moving core, it is a rotary moving core. So the remaining rest of the construction is same as LVDT, and you can see the secondary winding 1 and secondary winding 2, and this is the primary winding. So in between this, it is rotated, and it is a rotary type LVDT. It is also used in many practical applications. So these are the two types, LVDT as well as RVDT. RVDT is rotary variable differential transformer. So advantages of LVDT: high range of measurement of displacement ranging from 1.25 millimeter to 250 millimeter. So here range is a little higher only, 250 meters, 25 centimeter you can measure. The absence of friction between the coil and core of an LVDT, there is no contact. There is no contact between the core and the coil, so no wear out. So infinite mechanical life we can achieve here. The separation between LVDT core and LVDT coils permits the isolation of media. The LVDT gives a high output, and many a time there is no need for amplification. So the output from the LVDT itself is readily usable, and in most of the cases the amplification signal conditioning is not necessary. High sensitivity, which is typically about 40 volts per millimeter, and these transducers can usually tolerate a high degree of shock and vibrations, especially when the core is spring loaded without any adverse effects. And LVDT shows a low hysteresis, and hence repeatability is excellent under all conditions. Low power consumption of LVDT is very less than 1 watt. So 1 watt, it is power consumption is also very low, and that is another big advantage. So coming to disadvantages of LVDT, it is relatively large displacements are required for appreciable differential output. So here the output to get the readable or understandable output, we need a little larger displacements. They are sensitive to stacked magnetic fields, but shielding is possible. So any magnetic material comes nearby the LVDT, there will be adverse effects, and shielding should be done properly. The transducer performance is affected by vibrations. The receiving instrument must be selected to operate on AC signals or a demodulator network, which must be used if DC output is required. So the dynamic response is limited mechanically by the mass of the core and electrically by frequency of the applied voltage. The frequency of the carrier should be at least 10 times the highest frequency component to be measured. Temperature affects the performance of the transducers. And users applications, it is used to measure displacement, force, weight, pressure, thickness, etc., etc. And for this you can refer these two books. One is A.K. Ghosh, there is Bolton is another book, and this is A.K. Ghosh, Instrumentation in Introduction to Instrumentation and Control. Is a really very good book. You can refer this book. Bolton gives the concise way of any instrument, and he has not explained much in depth. If you need more details, please refer A.K. Ghosh book. So we stop here, students. In next session we will see the strain gauge. It is also very important topic in exam point of view, that we will discuss in coming session. Thank you.